Let's use an example now to give us an idea of the size of a scale of a single farad. So we have a parallel plate capacitor. It has a capacitance that we'll say is 1 farad, and the plates are 1 millimeter apart. And that's not an atypical distance for capacitor plate spacing. What's the area of the plates? So to write our list, we know that the capacitance is 1 farad. The plate spacing is 1 millimeter, or 1 times 10 to the minus 3 meters. And we're going to try and find the area. We'll write down our equation for capacitance. It's epsilon naught, the permittivity of free space, divided by the area, divided by D. Let's rearrange and solve for our area A. That's going to be the plate spacing D times the capacitance divided by epsilon naught. Plate spacing D is 1 millimeter times the capacitance of 1 farad. And then we're going to divide by our epsilon naught, the permittivity of free space, 8.85 times 10 to the minus 12. Now, let's just sidetrack momentarily about the units for epsilon naught because units can help us stay on track. Epsilon naught is our permittivity of free space. It has units of coulombs squared divided by newtons per meter squared. Now think about that for a moment. That's the same as coulombs squared divided by a newton times a meter. Times a meter. I just broke up my meters and put brackets there. A newtons times a meter is a joule. So epsilon naught, coulomb squared over newtons times meter squared, is the same as coulomb squared per joule divided by meters. Coulomb squared over joules times 1 over meters. Coulomb squared over joules, that's a farad. So the units of epsilon naught can be written as farads per meter. Okay, so sometimes a unit analysis can really help us make sure we're staying on track. Let's go back to our problem now. We do our division on our calculator and we get 1.13 times 10 to the 8 meters squared. Okay, we've got our list. Let's take stock. Is this a reasonable answer? Well, if the area of our plate is 1.13 times 10 to the 8 meters squared, that's the same as saying our capacitor plates are 10.6 kilometers on the side of a square. So I gotta say, a 10K capacitor is not very a reasonable size. Okay, so I don't think this is a sensible answer. So let's make sense of this. What is this telling us? First thing is that capacitors and capacitance is generally very small. So one result is that 1 farad is very big. And typically capacitances are on the scale of microfarads. That's 10 to the minus 6 farads, to picofarads, which is times 10 to the minus 12. So when we do capacitances, we're typically going to have somewhere between a power of minus 6 and minus 12. So normally capacitances are pretty small. The next thing is we can segue this into dielectrics. So if we look at our equation for capacitance, we had epsilon naught in it. That's because we were talking about a capacitor that just had air between the plates or vacuum. What would happen if we did have something between the plates? What if it wasn't just a vacuum? Then our equation for C, it wouldn't depend on the permittivity of free space. It would depend on the permittivity of the material because the electric field wouldn't be just going through a vacuum anymore. It would be going through the material between the plates. A benefit from putting a material between the plates is, remember, if we have a high potential across a distance, we end up getting a breakdown of the air and it makes a spark. We talked about that when we talked a little bit about lightning. That can happen in a capacitor too. If you get a high enough potential across those plates, you'll get a spark jumping. What happens when you have a spark in a circuit is it can burn the circuit right out. So of course that wouldn't be ideal. When we put a dielectric between the plates, it changes the capacitance and it reduces the effect of that possible breakdown and sparking.